We're going to talk about the actual VM. We're going to talk about the actual state of what you could and couldn't detect on it, what all was changed, that sort of thing. But first I want to start with the chaff that I put in there just to basically fill it up so that if you ran something like Gmer, you would see a ton of results and you would have to filter through them. You would be encouraged to remove stuff, right? So if you know that this change is due to zone alarm or daemon tools or something like that, you would want to try to get rid of that. If you were going to reboot, you'd try to uninstall stuff, something like that, so that when you reboot, you can get back to a clean system and see, did those changes go away? What do I have to see now? Like on a clean Windows system, these things like Gmer are not going to report anything at all. Yeah. So the software installed as chaff were control to cap, so that was to do device attachment. So we talked about IRP hooking. We said there's the device object chain of the things which want to hear about IRPs. And so control to cap was just to have something attached to a device, just to make sure that I had that in there if I didn't get that through any other means. Daemon tools, I found this previously on John's system. It looks very much like a rootkit, and it does a bunch of stuff like the IDT hooks, SSDT hooks, hiding the file on the file system. What else did it do? I don't know, IRP hooks. It just kind of does a little bit of everything, and it's, quote, legitimate software, right? But it's that SPTD.sys that's the main component which does all this stuff. And no, I don't remember what I was going to say about that. But definitely uninstalling that would make your life a lot easier for filtering out the noise from the signal here. Zone alarm, again, SSDT hooks, things like that. Also IRP hooks, everything else. But so zone alarm, as you know, it's a firewall. Oh, I know what I was going to say about daemon tools. The STPD or SPTD.sys, it's trying to do emulation of an ATAPI device where it's trying to, that was another reason why I originally thought it was like TDSS, because TDSS rootkit infects ATAPI.sys, the thing which talks out to the CD drive, for instance. And this thing, Daemon Tools, also makes it look like there's an infection in ATAPI.sys. But it's basically trying to pretend to be a CD drive so that when DRM software is executing on the CD, so if there's music CDs that have DRM software on it, where they'll only allow you to play it if there's not certain things found, that's basically what it's trying to do. It's trying to hide itself so that it can allow you to rip the music off the CD even if there's DRM in place. So zone alarm then is just a host-based firewall, and trusty rapport, like I said, it's trying to detect keystroke loggers, trying to grab your credentials for your bank account or eBay or PayPal or stuff like that. All right, so for instance, control to cap by itself is nice and simple. It just shows up as something that's attached to the keyboard class 0 device. And so specifically, it's an upper filter driver on keyboard class 0. Now, trustier rapport, on the other hand, has things like SSDT hooks, inline kernel hooks, so actual inline kernel hooks, that's funny. Inline user space hooks with DLL injection and IRP hooks. So here we've got, this is just, I made a VM and all I did was I installed trustier, and this is what I got. A bunch of SSDT hooks right there. This right there is a inline hook in ntkernelpa.exe, 7-byte jump instruction. And then a bunch of inline hooks in user space components, so it injects the DLL into user space and it hooks things there. All right, zone alarm by itself. Bunch of SSDT hooks again, things like connect port, create file, create key. It also has an inline hook in the kernel, ntkernelpa.exe. So let's see, inline hook in the kernel, just one. And then again, it's doing user space DLL injection in order to put itself in the memory space of everything and start putting inline hooks there. And I say that's all, but I think when I went back and looked with I think, didn't we say when we looked with virus block Ada, we saw extra stuff like export address table hooking of Endis and things like that. So there may be some more information that virus block Ada said about what this is doing. Yeah, so this is just, I just pointed this out because it's sort of interesting. This is not your standard inline hook. Normally an inline hook has like a jump instruction or something like that. This has a shift right, byte-wise shift right. Well, I'm not entirely sure how to interpret that. And this may not be the correct interpretation too, I should say. Because it's starting to interpret the instructions where the changes were made, but they could actually be incorporating bytes from the previous instructions as well. But if these are correct interpretation, which probably would be a good idea to go to kernel and confirm that, then it's interesting because it ends in an interrupt 1. And interrupt 1, like we learned from intermediate x86 class. Can you grab the door? Thanks. Like we learned in intermediate x86 class, interrupt 1 is a debug interrupt. So that's for hardware debug breakpoints. So hardware breakpoints or things like where they're trying to stop people from changing the debug registers and things like that. So if this is actually ending in an int 1, that would be interesting. All right, zone alarm by itself. All right, there's also a bunch of IAT hooks. So in both kernel space, yeah, so this is where I said there's also export address table hooks, but Gmer is not showing them, whereas virus block Ada did. So import address table hooks in kernel space and tcp/ip.sys, wanarp.sys, basically some network components. And then IAT hooks in user space, where again it injects itself into everywhere. Hooks load library. Looks to me like the only thing it hooks in the import address table in user space is load library. So it's worried about people adding new DLLs, opening new DLLs on the fly. And then finally at the bottom, these device ones, that was where we said it's hooking the major functions of the IRP, major functions of a driver object. So we've got driver object, it's got those 28 function pointers tacked onto the end. And this is just the very abbreviated version of that, where it's saying if you were to go to driver object tcp/ip.sys, which is associated with device object /device/IP, you would see that the function pointers are being hooked there. And specifically, those function pointers are targeting versus data nt.sys, which I don't think I've said in this class, but although this is being used with zone alarm, I'm pretty sure that this is actually awesome. My computer seems to be crashing. Versus data NT, I'm pretty sure this is a third-party module actually that people can license, because this is also a component of Cisco VPN. So if you start up Cisco, this versus data NT gets loaded into memory, and it actually doesn't unload when you quit Cisco VPN. So like Cisco also uses another third-party software, DNE2000.sys, which I know that one is definitely something that you license as a subcomponent. It's Deterministic Network Enhancer 2000. That's a component that Cisco licenses. And so I think this versus data nt.sys is also a licensable component, but not 100% sure on that. All right, and then finally, this is implying that as a consequence of zone alarm loading, the filter manager.sys component is getting attached to the fastfat driver object, I believe. So this is the driver object, that's the device object. So the driver object is the fastfat, and device object is fat. All right, and then so here is daemon tools just by itself. So specifically the sp_td.sys. So there's only a few, like whatever it is, 7 SSDT hooks. There's some IDT hooks, but the interesting thing is that these IDT hooks don't point at the SPTD driver. So maybe it created some dynamically allocated memory, copied some code there, and then pointed the interrupt descriptor table at that location. I haven't actually investigated that. Also interesting is that they both point at the same place. Then there's some actual self-modification that looks like it's going on. So the .text section of sp.td.sys is marked as having a 32-byte change and a 4-byte change, et cetera, et cetera. And so this looks like a place where the thing actually went in and modified its own code. Gmer can't find any instruction sequence that this makes sense. It's trying to like disassemble this. So in this one case for this 4-byte change, it tried to disassemble it and it got a jump 0, whatever that is, negative 15. And then it got a jump above negative, whatever, 3. But mostly it's just seeing a bunch of bytes that are changing and it can't figure out what instructions those are. So it could be some self-modification of data, could be something else, but since we know this is a clean system with only sp.td.sys installed, we know that there's no other rootkits or anything that are coming in and trying to change it. So it must be changing itself in memory versus on disk. Then there was that one heuristic that Gmer has that I pointed out, where it's saying the entry point is in .sp.td2, saying this is a section that's named something other than .text. So that's sort of abnormal. Most of the time, your entry point always starts in the .text section. And so the reason why that might matter is, for instance, TDSS, like I said, it infects the atapi.sys driver, sort of virus-like. So it attaches its code into the resource section, if I remember correctly, and then it redirects the entry point in the P headers saying this is going to start down here in the resource section where I attached my rootkit code, rootkit/virus code. Then we've got this AE3R blah blah blah.sys. This is that randomly named driver that it creates each time it's changing the name of the driver. And it's saying, and Gmer's saying, you've got some driver that's loaded, but I can't find it on disk where it says it's supposed to be. So according to internal data, it says it should be system32 drivers, that name.sys, but Gmer can't find it at that location, so it's saying that's suspicious. Maybe it hid itself or something. Actually, I know that this one did hide itself. If you go to the location in explorer.exe, you'll see it's not there. And other things like import address table hooks, device hooks. You can see that this is fairly aggressive in that it changes a bunch of locations in the major functions. There's the rest of the device hooks. And finally, there's a bunch of hidden registry things. These are a little bit more advanced than, well, not more advanced, just more extensive than the hidden, just Hacker Defender. It hides its service in the current control set services for Service Control Manager. But this has like a bunch of different registry keys throughout the system that it's hiding. Or, I mean, it's certainly hiding its, you can see that this path does have current control set services SPTD, so it is kind of hiding its service there. But there's extra information as well. It's creating extra keys that it wouldn't necessarily have to, these config keys, which I would wager these have some sort of configuration data that it's trying to put in the registry and then hide it so that it can't be manipulated. And so the only thing, okay, this is just, I guess, a different screenshot where I right-clicked, I selected option, and then I selected IRP hooks just to tell it be more verbose instead of just saying, that device changed and that device changed and that device changed. I'm saying actually now show me every major function and where it points. And so it turns out that they actually all mostly point to the same location. Those two differ, which is interesting. All right, so that was daemon tool. So this was the chat that I installed in there. You can see lots and lots and lots of changes just related to all the chat, right? But this is kind of meant to be realistic in the sense that if you show up at some random box that someone has been allowed to install stuff on for years, it's going to look like this. And this is why, while it's good to know these tools to go apply to something like a home system, you're going to have to contend with this chaff, and you need to know that there's security tools which are doing this, and they may not always be attributable who's doing what change. right? Like these interrupts here. If you were to see nothing else, if you were to not know this was due to sptd.sys, and you see all these things and you say, okay, well, I know all those changes look like they're basically dealing with sptd.sys. I can ignore those. That's daemon tools. I expect that to be there. But for those other changes, they're not attributable to that particular driver. And so you're left with the question of, how do you figure out whether those are good or bad? You can go in and start reversing them, you know, pull up WinDebug, do a local kernel debug session, go to that address, and start looking at the code and see if you can find anything that jumps into sptd.sys, at which point you can say, okay, that looks like that's probably okay. Otherwise, then you have to do something like uninstall this and see if it goes away. And then you can again say, okay, that was associated with this. And so this is still somewhat of a hard problem when you're dealing with single systems. That's why I kind of advocate for the importance of applying, at least for, you know, bigger systems like corporations, it's important to be able to take this sort of data about all your IDT entries across the menu systems and correlate them by, you know, just starting with the simple case of doing histograms. So you can say, across all of my systems, where does SSDT entry 0 point? Where does SSDT entry 1 point? Of course, you can't use the absolute addresses. You need to use like symbol names and stuff like that. But that's, I don't want to get into that. All right, so that was all the chaff changes. So now here's all the legitimate changes which you could have potentially found as part of the homework. And again, I will be distributing the anonymized homework thing so that you can see how different people came at it. You know, I really am liking these write-ups thus far because people are coming at it from a lot of different ways using lots of different tools. So one person knows about, you know, Gmer, he uses that. Another person knows that he can boot from a Knoppix CD in order to check the hard drive. Another person already knows about volatility, they're going to use that. Another person knows about, you know, another person just throws antivirus on there and sees what they detect, because some of these proof of concept rootkits are plainly detectable by antivirus. So these are the actual changes that are attributable to me. So ShadowWalker and Futo have to kind of be used in combination, because if Futo is not already on the system at such time as I start up ShadowWalker, ShadowWalker is actually looking specifically for msdirectx.sys. So it's looking for that, and then it's going to start intercepting page faults so that if you try to read that thing's memory, so if you were to try to go to this memory, F065, blah, 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 it just points you at some junk memory space. Now I say that, and you know, per that ASCII art of doom, you'd think it would be pointing you at some memory which has garbage data in it. When I've tried actually looking at this stuff, it seems like it's not, I don't know if it's maybe just not handling WinDebug or what the deal is, but when I've tried actually going in and looking at the memory that's being hidden with ShadowWalker, it always just shows up in WinDebug as not mapped. So WinDebug says I can't find any memory at that location, which to me implies WinDebug is seeing the page bit is, the present bit is still set to not present. So I don't know whether it's actually supposed to be redirecting to junk data or not, but at least in WinDebug, the data is, quote, hidden still, because when you look at that virtual memory address, for instance, F065, blah, 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 with WinDebug, it'll say, sorry, there's nothing there, but we know that there is actually something there. All right, so these are the changes. This one was the one which I had to issue the correction on. Process hidden, this is saying process ID 0, but in reality, the reason this didn't make sense to me is because when I issued the Futu command in order to hide it, I actually hid process ID 4 because doing 0 wasn't working for me, and I was like, okay, well 4 also looks like system, so do that. So that's the hidden process, and then I called Futu in order to hide each of these things manually. ShadowWalker installs an interrupt hook right there, and then I believe, I'm not even going to speculate why it thinks that the MS-DirectX is hooked. I'll just say that's what would have showed up. Basic hook hide file. This was something where it's just trying to do the most basic of SSDT hooking, and it hooks ZW query directory file. So it's only one thing. As you saw that all of the commercial software, you know, they've got a bunch of stuff they want to hook. They want to hook registry stuff. They want to hook file system stuff. They want to hook network stuff. This is just, you know, very proof of concept. It only does one thing, hooks the listing of directories, which can be done through ZW query directory file. And it intercepts that, and then it checks for every listing of directories, is there a file or directory within this directory that starts with _cool. Okay, so I just made an empty file called _cool_beans, empty directory rather. Named _cool_beans in that directory, and now anything on the system you can go in, create a text file called _cool whatever, and you know _cool.text, and it will just magically disappear because this thing control to cap, you know, fake control to cap. I just named it control12cap.sys in order to look like the chaff, right? So we know that we had this chaff installed. You would have seen, okay, control to cap's there. It's the Windows NT caps lock swapper by sysinternal. So you would have maybe seen this and then said, okay, Google it. Looks like a sysinternals tool, so that's all fine. And you maybe would have then seen that it's doing SSDT hooking and not noticed that the 1 is a 1 instead of an L, and you would have just said, okay, well, I guess control to cap also does SSDT hooks. That was just a hiding in plain sight ploy, because it's not actually hiding its own file and file system. It's only hiding cool files. All right, Vanquish is one of the more, you know, robust things. So basically, out of all these, there's Vanquish, Hacker Defender, and Key for Hook. Those are ones where they were actually kind of weaponized to some degree. They're meant to be, they can actually be used as attacker tools. The other ones are just kind of proof of concept where they say, here's how you hook SSDT, and this is how it hides files. So Vanquish is a user space rootkit, ring 3 rootkit, where it uses DLL injection, which we already saw. A bunch of our third-party software does that as well. But it uses DLL injection, and then it does inline hooks. So it does .text hooks into kernel32.dll, looking for load library, create process, etc. Reg close key, reg num key. So I can see based on this, all right, it's hooking registry access, it's hooking process creation and library loading and stuff like that. I would expect to see something also having to do with file system padding, but it's not jumping out at me. Oh, there it is. Find first file. That's probably what it's using for, and find file next. Those are two things you can use to enumerate the files in a directory. So it's hooking those, and therefore it can hide files. Right, so the GMER results are saying, one, it's got all these inline hooks, and there's like a ton of inline hooks in all the processes, so I just didn't show them all. 2, it's hiding this file, Vanquish -021. So again, remember, I went into a VM and I only ran Vanquish. So in this VM that I took these screenshots at, it worked. On your VM, it probably wouldn't show those as hidden. You'd just see them in C:, Vanquish. But still, I expected you to find C:, Vanquish and be like, what's that? Google it and say, yeah, I found Vanquish. All right. It also has some hidden DLL. So actually, part of the thing is when it injects that DLL, it will also hide it using decom. So there's a list of loaded DLLs within a process's space, and they just unlink the Vanquish DLLs from within there. So you can see sort of these, 3 entries repeated. So in each different process, so in VMware Tray, VMware User, CTFmon, etc., in each of these processes, it's injected itself. These DLL components get loaded at 1AE, C7, C8, 1AE, 3F, B2. So some of those are dynamic. It looks to me like the actual DLL is this hard-coded address, the 1AE, because the DLL has a preferred base address, right? In the P header files, it says, here's my image base. And if that's not already taken, if that virtual memory is free, then it gets loaded there. And for these other two things, I would expect those are dynamic memory allocations, which it's also hiding.
So is the Vanquish VM aware of that, or?
Is it VM aware?
So,
No, I don't think so. No, those are just some user space processes that it happens to inject itself into. So it's just saying, You know, I mean, it's injecting itself into basically anything that starts up. It's not everything, but most things. All right, and then it's got a hidden service. So when it's working correctly, you would see Vanquish auto start service is in the registry, but it's being hidden, so it's hiding the registry key. And then there's a bunch of other registry keys that it's hiding in. Do I have more? No. So the only registry keys which it looks like it's hiding are the ones pertaining to its current control set, services, Vanquish. And then these are the individual fields: type, start, error control. Those are the service control required fields. All right, so that was Vanquish. Then there's Hacker Defender, another user space rootkit. Therefore, it's using DLL injection plus import address table hooks, inline hooks. I don't think IAT hooks, just inline hooks in this case again. So again, we can guess roughly at what it can do based on what it's hooking. All right, hooking create file, hooking device IO control, enumerate key. So it looks like file system access, registry access, file system access, system information. Query system information, that's where it can pull information about, like we saw in the Life of Binaries class, that's where you can call that in order to get the task list, but you can also get a bunch of other miscellaneous stuff. So it could hide itself in the process list by intercepting that. Read virtual memory so that I can hide virtual memory. Ah, yes. And then also some network components out of here. So there's WS232, that's WinSock 2 library. And so I don't think so, yeah. So it's not shown here, but actually in the configuration, and this is, I just left it the way that the configuration is that was in your VM. I think Hacker Defender has some capabilities that I actually wasn't using. One of them that I did add in late was I changed its config to say hide the fact that there's something listening on port 4500. Now the thing that's listening on port 4500 is just a legitimate system service, but I used Hacker Defender to make it so that if you run netstat in the system, you won't see that port 4500 is listening. And most of the tools don't show that, so I added that also as a late column in my rootkit detection comparison matrix. So I showed which tools can actually show you there is a hidden port right now. Because one, Hacker Defender does actually have a backdoor port that's running, and if you look at the anonymized write-ups, someone did Google Hacker Defender. They said, hey, it's got a backdoor port. This thing happens to be using default passwords and stuff like that. And they said, okay, I can connect to that. So you could connect to this backdoor port within your VM. But beyond that, there is also the ability to hide this listening port on the system due to its hooking of network functions. All right, so this is mostly inline hooks. There's one instance where it's saying there's some file that I see referenced in memory, a kernel driver, where I can't find that on disk. So it's just going to say cannot find it. That's suspicious. All right, then when we get to the end of the inline hooks, we see a hidden process. So it's using DCOM to remove itself on the user space side of things. It doesn't have to, it doesn't actually have to like go unlink things necessarily in the kernel in those eProcess structures. It can just on the user space side of things remove itself from results coming back. So hidden process, I don't know about this hidden library. That kind of seems like an error to me, but maybe not. And then hidden service, because as we said before, there's two service control manager mediated services where those are the things that actually started up at boot time. But it's hiding registry keys in order to make it so you can't see the services. But the interesting thing is that it also goes a step beyond, and it marks itself as its service is appropriate for running in safe boot. So you know that sometimes you think, well, I'm going to boot Windows in safe boot mode, and you think, all right, well, a bunch of the stuff, all of my third-party software will stop being loaded in safe mode, right? The answer is no. Things can register and say, I'm something that should still run when you run in safe mode. Beyond that, I don't think it's saying it here. And I don't remember if I'm just getting this off of someone's write-up or what, but I'm pretty sure Hacker Defender has the capability to infect system restore files. So, you know, you have the capability to roll back Windows to some system restore checkpoint. Hacker Defender can put itself in that restore so that when you roll back to that, you're rolling back to having Hacker Defender installed. So this was, you know, one of the more advanced user space rootkits. The person actually sold private versions of this, which bypassed AV, and so it was well known for being highly functional. All right, and then it's hiding any file that starts with hxdef, so it hides its own folder as well as the files within it. All right, so that was Hacker Defender. Then there's Basic Callgate, which, as we said, the only thing it does is install a callgate, which you can see with Toluca in the GDT, or you can use WinDebug descriptor plugin from Intermediate x86 to dump the GDT, or you can use Volatility. There's a GDT command in Volatility, which you can use to dump GDT. That'll also show callgate. And not quite finally. Then there's sysenter hook. This, all that did again was it went, changed the relevant MSR, IA32 sysenter EIP, changes that EIP so that when user space calls to kernel space using the syscall instruction, or sysenter instruction, when user space calls to kernel space, it points at the attacker's code in syse.sys, or I think in your VM it was sysenter.sys. And therefore, the attacker can now, you know, sit there and say, okay, what's EAX? What function are they trying to call? It can say, oh, it looks like they're trying to call open, you know, ZW query system information or something like that. You can man in the middle of that. All right, so I think this is the last one, key for hook. One thing is, like I was saying, there's a bunch of these shutdown objects, which I believe it's actually overriding existing shutdown callbacks. So for all these things on a clean system, there were these object names, and they were pointing at legitimate system things. And it looks to me like Key4Hook is going in there and overriding those in the actual array of callbacks. It's saying, you know, nope, call me, nope, call me, nope, call me. It's just overriding it, and, you know, probably copying the original handler off to the side. But the main things that I had noticed in the code were the create thread and create process. Really only the create thread is the one that stuck out at me. So these are so that when new threads are created or new processes are created, Key4Hook can find out about it and, you know, potentially modify the new process. So overall, though, like we saw before, I showed those jobs that were run in order to hide SQL and Windows System 32 drivers foo.exe. Okay, wait, that's, yeah, so I don't have a good Gmer snapshot of that, but one of the changes you would see is that there's the hidden foo.exe file, because we said Key4Hook, we brought it in as a, you know, extra cover-up for Futo. So Futo loads, does its thing, it hides itself in memory. Key4Hook does its thing, hides Futo on disk. So that was one of the things. Other things were these callbacks. And then also it hooked a ton of IO request packet major functions. So for all these driver objects here, so the driver object is CDFS, NTFS, FastFat, whatever, VM, HGFS, mulp. So it's, oh, well, those are actually the, okay, so that's a bad screenshot. Those are the other types of function call handlers that I said we weren't going to talk about in this class. Fix that, but Key4Hook basically is responsible for at least for NTFS, I believe CDFS and FastFat, sort of similar to Stuxnet. It goes in there. There's a few more beyond that, but it goes in and it changes the major functions in the driver object, so they point, all of them point to Key4Hook. All right, and finally, there's this other thing which you can see through volatility or through virus blockade. One heuristic that can be used in order to find code which is executing from dynamically allocated memory is what you would call an orphaned thread. So it's saying right now I can see that there's a thread, there's a thread data structure. This is thread ID 208. Oh, sorry. Down here, saying the thread originally started at this address 814 blah blah blah. The thread data structure is that address. This is the thread ID. But it's saying there's no corresponding module for this address. So this thing started at this particular address, but this isn't anywhere inside of a kernel driver, for instance. So it's saying there's a thread that's executing out there on the system, but it has no actual driver associated with it. And so we know the reason for this is that the system got started up, key for hook copied itself to dynamically allocated memory, and then it just unloaded its driver. But still, this code is potentially running, and it's running in the dynamically allocated memory space. So you can find that with virus block Ada or with volatility. Volatility has an orphan thread scan, which will find that. And that'll kind of give you addresses where you know there's code executing at this address. So you can go analyze the code at that address and see what's actually going on there. And like I said, the only tool out of the ones we've looked at that I know of that can actually detect key for hooks, extra SSD key stuff that it tacks on is volatility. So this was the volatility command. When you did the SSDT command, you saw that there were 5 entries in, index 2 of the SSDT, whereas index 0 is the normal SSDT. Index 1 is potentially the shadow SSDT if you have graphical routines. But index 2 should either be IIS or it should be nothing. So the fact that there's something here that's not IIS shows up as suspicious. All right, so then I have this rootkits, the WinDebug cheat sheet here at the end. This probably I'm going to keep working on this a bit because this will even be useful for me so that I can have one single place that I can go for all of my commands. I'm not going to go through all these. Just you can play around with these when we have lab time here in a second. So you can do check image on ntkernel.exe and see what shows up for changes. All right, so I'm going to go ahead and go all the way and go through my closing ceremonies, and then we'll have lab time where you can use these tools some more on your VMs, ask me any questions. I'll just sort of be wandering around for a little bit if you have any questions on tools or anything. All right, so it's unheard of that I'm getting done early with the class. I guess McLean must have asked a lot more questions or something. But so the main stuff which we learned in this class are, one, what are the appropriate tools when you sit down at a machine and you're asked, find if there's something bad going on the system. I think the tools that are appropriate for, finding these kind of malicious modifications to the system are things like Gmer, Tuluka, virus block Ada, if you're actually on the system. So these are the kind of things where you potentially bring them home to grandma's and you run them on her system and you say, okay, well that one, Gmer says that there really is a rootkit installed, so let's start rolling back some of those changes, or let's get rid of the sys files that are associated with it, right? Let's maybe try to unhook everything, and then now no longer can this thing prevent me from deleting a file, for instance, and now I can delete the file so that it's not going to persist. Or if it does persist, you reboot, and if you still see changes, well, then you need to go hunting for some more locations that you may have missed. So we saw tools for in-system analysis, looking for rootkits. We saw WinDebug for live debugging on a system where if you want to go in and actually look at the code and analyze it, you could. Well, on a live debugging session, you can't set breakpoints. So you can't just set a breakpoint and let it run and see what happens. For that, you have to have a full debug session. For WinDebug, when you know what you're looking for, you can go deep with it and dig down into the data structures. In some cases, you may want to use WinDebug to fill in for other things. So We know that a limitation of Gmer and virus block Ada and Toluca is none of them are K-interrupt aware. So the question is, if you see some change reported by volatility and it's saying, okay, this IDT entry is, doesn't point at anything, you may have to go in there and use WinDebug to say, is this a K-interrupt? And if it is, okay, is anyone hooking the service routine? Doesn't look like it. Is anyone hooking the dispatch routine? Doesn't look like it. Are there any inline hooks inside of the thing? Well, that's a little harder to check for. You're probably going to have to dump the memory. There's a WinDebug command to dump memory, and you could dump the blob of code that's stuck on the end of the K-interrupt. You could dump the template code from where it's copied, and then when you dip those things, there should just be 2 instructions worth of difference, and that's natural difference. And you could sanity check that as well, but probably would be going a bit beyond what would be expected. All right, and so then we just learned about, we learned about applying each of these detectors to different types of modifications to the system, type 0, type 1, type 2, type 0, yeah, type, I'm forgetting. Did the stealth malware taxonomy start at type 0? Or did it start at type 1? Type 0, yeah. So type 0, right, those were the things which kind of hide in plain sight. Some of the things, like I probably should even put auto runs on here as one of the important tools to look at. Auto runs can be useful for things which hide in plain sight, where if you know what should be starting and if you see something new that's starting, that's the kind of thing you want to look for type 0 stuff. For type 1 and type 2, that's where all the stuff like Gmer comes in. And type 3, we didn't talk about any, we talked about it, but we didn't show or install any hypervisor-based rootkits. So, so not so much on the tools for doing that. Hopefully in a future class, speaking of David, hopefully David will do a future class, an advanced x86 class, where we learn about hardware support for virtualization. And if he builds such a class, then he will, if he builds a minimal hypervisor, then he will have rebuilt something like Blue Pill, right? And so Vitriol would be the x86 version of that. Or was it Subvert? I think it's Vitriol. So if there's an advanced x86 class specifically talking about hardware support for virtualization, then you'll build a little hypervisor, and that little hypervisor then could potentially be a Blue Pill type thing. So we'll see on that. I'm trying to start getting, for the advanced x86 classes, I want to potentially go down multiple paths. So I'm asking people like David to cover some of those paths, and I'll do one, and he can do one, and maybe John will do one. See? Right, so these are the main types of changes to the system that we learned about. Interrupt descriptor table, we'd already had familiarity from intermediate x86 class. Import address table, covered that in life of binaries. Inline, all that really means is just putting some new assembly instructions overwriting existing things. But then the new things were stuff like SSDT, sysenter, and IRP hooking. SSDT, that's the table of functions which are exported from user space to kernel, or sorry, that kernel exports as an API for user space to call. Sysenter, that's the way that you get from user space to kernel space. And IO request packets are a Windows-specific mechanism that it uses for abstracting IO going into and out of the system. Those were sort of the type 1 kind of things. Actually, I don't remember what the point of this division between these two was. We also covered the call gates, which again is something we said was added into this year's intermediate x86 class. Direct kernel object manipulation, where Futo was hiding kernel drivers or processes on the system. Kernel object hooking, thankfully we got there, and we talked about stuff like decay interrupts or those NDIS structures or object type initializer structures, where if the attacker knows more about the system than you do, they can come in and start targeting specific data structures which have function pointers in them. And there's a bunch of other ones beyond what I've shown here, but they're at the references that I linked at the appropriate section. All right, and then kernel callbacks and bootkits. Kernel callbacks, this is the sort of legitimate mechanism that Microsoft is exporting, saying, look, I know you want to hear about all the registry changes. Security software needs to needs to find out what registry changes are made or file system activity occurs. Here's the function. Call this function and give it a callback address. And when a registry event occurs, it will call you back at that address. And so that can be used by security tools, and that can be used by rootkits. And then we also talked about rootkits. And we said that, you infect the master boot record of a system, and they kind of bounce their way up the chain so that they keep changing the stuff before it loads, so that ultimately you lead to something like NQS kernel is modified before it loads to turn off to turn off code signing or turn off patch guard, or in the case of the original EI boot root, it just modified ndis.sys in order to get a little backdoor so that it would look for specific packets. All right, so that was the overview of all the kind of stuff we learned. The materials that I'm going to be sending to people are these slides, so you can review these. They're obviously updated from what got sent to you at the time that I had to print them. It's going to be the anonymized write-ups, which I definitely recommend people check out. You'll see little tricks that other people, how they approach the problem, doing things from like file system forensics perspective or memory forensics perspective. Just everyone came at it a little different, and there's definitely useful information there. All right, then the spreadsheet, the comparison matrix. I'm going to maybe leave this up on the board, and you can use this to decide what tools you want to play with when. But this is the little comparison thing saying what can detect what. I'll be sending that out. And actually, maybe I'll use this time here at the end to add one more thing. There's a Chinese tool which I found out about that looks like it has really good capabilities as well. I just need to add it into the matrix. All right, so I'll send you the spreadsheet, slides, blah, blah, blah. TiddlyWiki, this is kind of meant for use by instructors, but it's also useful for you in, let's see, in the case of if you want to drill down more into how you would actually determine that something is or isn't a rootkit, that's the RE rootkit section. So here you can dig down into 3 examples where I dug in and I said, here's a change, and here's how I determined whether it was or wasn't malicious. I think I have like 1 non-malicious and 2 malicious, I think. So you can dig into that if you'd like, if you're comfortable with the x86 to understand the instructions. And then the other thing is the setting up the lab, and this is basically the instructions for what commands you actually use. And towards the end, I mean, this is how I wrote it at the beginning, but towards the end, I just, let's see here. Yeah, I just pretty much said, here's the instructions I issue in order to install the code. So when I was, this omega.bat is my large bat file where if you were, if you have the appropriate drive mounted, so I have this rootkits folder which I'm going to send you. It's going to have the installed rootkits. It's going to have just random stuff I pulled down from rootkits.com and other places. So if you were to mount these into the VM and then issue these commands, you would be able to install all the rootkits. Yep, just by executing all these commands in sequence. So you can kind of recreate the things. If you want, you can basically go to a clean VM, mount, over the network, your local host or whatever, have the rootkits folder shared, and then just do these commands to install one thing at a time, to look at them, or to install new stuff that I didn't put in there, like hybrid hook or whatever else. Just pick some stuff out of the rootkits.com mirror, which thankfully I made a little while before they had the whole HP Gary debacle. So I've got most of the files that I didn't grab everything, but most everything that looked relevant to me I pulled out of there a couple weeks earlier. All right, so there's that. And, yep, so then the collection of rootkits. I'm going to send you a folder. That one you do not want to download onto your miner machine. Put it on your personal machine if you want. Put it into a VM if you want. But I'll send you that through X-Files. That will have live malware things. It's not, I don't think there's any real in the wild kind of stuff, but that doesn't mean that the antivirus is not going to flag it. There's at least one where it's like a keystroke logger that I was thinking about installing, but the free version isn't as stealthy as the paid version. I had a version of the paid version when they had like a 1-day free trial thing. I downloaded it at the time, but I didn't want to install that one. So anyways, I'll send you all the rootkits and stuff like that. And you'll have the bat file from the wiki in order to install stuff as you want. But again, don't install the rootkits folder on your MITRE machine. You will get flagged. And then, so in the interim, you can, analyze, like at the end of today as well, obviously. You can analyze your existing VMs some more and, use different tools in order to see what they see and what they don't see. Get familiar with Virus Blockade some more because I think it's a good tool. But I'm going to be creating a VM. So this, again, was the scattershot VM. This is like get as many rootkits as I could get into the VM that would work with each other. So some of the things I modified myself, they wouldn't work inside this VM. And so I had to roll those back. So in the future, I'm going to be making not a scattershot VM, but a more tactical, subversive VM where the persistence is not as obvious. The manipulations to the system are not going to be as obvious. They'll all be stuff that are within the realm of this class, so I'm not going to go using some kernel object hooking technique which isn't even in this class. But it will be trying to be a little more stealthy about how it persists and how it hides itself. So getting familiar with the tools now will be a good way to try to detect that later. That's not a homework or anything. It's just going to be a thing where if you want to test out your new skills, you'll have a much harder thing to detect, and you can see how using still just these tools from this class and the knowledge, you may have to go line by line of the little offhanded comments that I have in these slides, but the new Rootkits VM will be using stuff from the slides. All right, so you are here, right? So hopefully everyone's already seen this at some point. Right, hopefully I know that not everyone's had these classes, but at mc.mitre.org, go to the content tab and then go to MITRE Institute. You can get the videos for all of these. These are each 2-day classes. I recommend checking those out. If you haven't already taken them, because I'm not going to teach them for another 2 years probably. This one I may teach again next year. It doesn't matter to you. You already took it. Reverse engineering, Matt Briggs, unfortunately for you Bedford folks, he's not going to be teaching that until the fall up here. So he's teaching that down in McLean, but can't teach it again until the fall. And then vulnerabilities and exploits, Corey is going to be teaching this, or if you're interested in exploits, that would be a good class to attend. This class was obviously focused on the what an attacker can do once they're on a system, to persist on the system, hide on the system. But Corey's class will be more about, the exploit side of things, how you get on a system. When you have vulnerable software, how do you exploit it in order to execute your code? Once you're executing code on the system, that's where you start, pulling down any additional code you'd like, installing tools, things like that. All right, so that is rootkits. Any questions before we have lab time? Yes?
Did any of the tools catch inline hooking?
Yes, so Gmerk caught inline hooking. It looked like it called it by the section where the hooks were found. So like right here, where it's saying .text, it's saying the .text is the section of an inline hook. vmtools.d.exe, that's the exe which the memory space is in. Kernel32, that's the DLL. So we're in the memory space of vmtools, but the inline hook actually occurred in kernel32.dll at the symbol read file. So this is the address that corresponds to kernel32.dll in that guy's process space. That's the name of the function. And then 5 bytes have changed, and there's a jump instruction where there shouldn't be a jump instruction.
Does it check the kernel?
Yes, it does check the kernel as well. This one didn't have any. Those were just 2 user space rootkits. But in our chaff examples, we had this one, for instance. Well, you can't see it on the board, but that's .text right there. So these are all .text. But this is .text, and this is nt-kernelpa.exe. And ZW callback return plus 243C. So that's saying some symbol plus some offset. So if it's like just at the symbol name, you know it's right at the symbol start. But in this case, it couldn't find a symbol name, so it went back to the next closest symbol, and it said that symbol plus some offset. There is 12 bytes worth of changes. It's C0, 6C. Those are the literal bytes that changed. It tried to interpret them as instructions. That's what it came up with. So yep, if it's an inline hook, it'll show up as .text or .page or something like that. The other one? Yeah, so here's a different one. This one has page, but that's just the name of the section. So if you looked at the PE headers for ntkernel.pa.exe, you'd see there's .text, .data, .rdata, page, page lock, etc. So it's just saying in the page section of this binary at this symbol, which corresponds to this address, there's 7 byte change, which it thinks looks like a jump instruction. Any other questions? Yep.
What happens when we throw 64-bit stuff into the mix? We've got 64-bit OSs that are becoming a lot more common now. Are there 64-bit rootkits out there? Are there any of these tools going to, is any of the knowledge for these tools going to apply to 64-bit systems?
Right, so most of the knowledge applies to 64-bit systems. Most of the tools tend to start breaking on the 64-bit systems. So yeah, the tools are absolutely not as good on 64. I know that Gmer has not been updated in quite a while. I mean, the author still responded to my emails, so he's still around. It's not like abandonware or anything. But the virus block Ada thing, because they're actively developing it, that's again why I think it's good. I know that in the latest release they added Windows 7 support and things like that. I believe I've used Gmer on like a Windows 7 64-bit system, and like a bunch of its functionality was grayed out over on the side. So it still could do things like checking the registry maybe, and searching for hidden processes maybe. But its capabilities were definitely scaled back. So the knowledge still applies because there is still an SSD key in the new things. It's supposed to be protected by the internal patch protection, kernel patch protection, aka patch card. It's supposed to be protected by that, but like I said, the TDSS rootkit is an example of something that installs itself as a bootkit. It starts up early in the system, and it does support x64 systems. It starts up early, and then it turns off those security features before the OS actually gets a chance to load, and then it can pretty much do whatever it wants at that point.
Volatility should be pretty good.
Yeah, so volatility, thankfully, now in this 1.4 release, so if you just go Google for volatility, most of the time you're going to come up with the 1.3 series, which does not have good support for anything except XP. And this was a little confusing because normally you Google volatility, you get to volatile-systems.com or whatever the company is that one of the guys made to do volatility-based training and stuff like that. But the 1.4 series, which is what you find from Google code links and which is what is linked to in your notes, the 1.4 series does have support for things like Windows 7 and newer, so Windows Vista and newer, things like that. So volatility will still be able to do analysis, but as you saw, in some cases volatility is making you figure stuff out yourself. In other cases, it will just tell you this is hooked, this isn't hooked. Yeah, so that's a good question. Definitely some of these tools. I don't have any 64-bit systems, so that's the problem why I haven't been able to evaluate how good these things are or aren't on newer systems. So that's like what we were talking about earlier today. I need to get a Win 7 system set up here pretty soon. Any other questions?
In the homework, and you guys a couple times removing the bad stuff once a time. How often would you actually want to do that versus just moving the system?
It kind of really depends on how confident you are in the results of these sort of tools, right? And how much attribution you think they're actually giving you. So depending on the rootkit, right? So let's say it was the EI boot rootkit, you would see that there's a hook in ndis.sys, but you wouldn't know where it actually came from. It'd be pointing at some code, but you wouldn't know based on that it actually started as a bootkit, for instance, right? So to me, as not someone who has a Windows machines at home, and therefore I don't really care. I don't have Windows machines I have to protect, so it's your problem. Personally, if I had, a running system where I wanted to, just remove some hooks, remove some kernel drivers, I think generally, I would say generally you can get away with if you can find the like .sys file or the exe file that is the thing. So if you see something like, Hacker Defender or Vanquish, they're user space things, they've got some exe or sys file which gets loaded up, and that's really where all the changes spread out from. When you can identify that sort of thing, you just remove it, and that's pretty much that, other than, those cases where it's infecting your rollback state, right? So I guess that really kind of comes down to your risk tolerance level. Right? And I'm fairly risk averse, but to me, it doesn't hurt to try to kill it once. And if you don't succeed and you reboot and there's still changes, well, then, oh well, you didn't succeed. Now you maybe need to nuke it. But if you removed, a few exe files, you removed some sys files, and you boot it up successfully again, you're not blue screening, and the changes look like they went away, generally speaking, that would seem to be good enough from my perspective.
One other thing too, when I was doing research, a lot of the older stuff mentioned offline stuff like that. And it seems like most of the newer tools are live systems. You think that live analysis is generally more useful than all?
It kind of depends on, well, I do think live analysis is useful. I think the fact of the offline scanning, and it really depends on how old you're talking with, like the old things that talk about doing offline scanning. It could be the case where when you're dealing with things, I didn't really cover the history lesson slides in this class, but when we're talking really old rootkits, they were originally just Trojan files where, you install a Trojan SSH daemon, you install a Trojan PS to list things so that you can't list your processes and stuff like that. And in those sort of situations, offline scanning or doing integrity checks over the file system absolutely made sense. Offline analysis still makes plenty of sense here if you have some reasonable baseline to compare against, right? So if you have a clean Windows system that you know it's clean for whatever reason, and you have a suspect system, doing offline analysis and doing the diffing between those is absolutely useful. It's just a question of getting the right tools set up in order to do the appropriate comparisons. Yes. All right. Any other questions? All right, then I'm going to pass these eval forms out, and then we're going to just start doing lab time independent